So today we're going to be looking at the question, a uniformly charged sphere has a radius r and a total charge q. It's a solid sphere. Find an expression for the magnitude of the electric field both inside and outside the sphere. Be sure to show your work. Also show at least one way you can see if your expressions are valid. So the first thing we're going to do is we're going to draw our sphere with our radius r. So we're trying to find the total charge inside. So we're going to draw a smaller circle within the sphere, since a circle will be easier to integrate when we use this Gauss's law. So since we have a plus q charge, we're saying that our electric field is coming from the smaller circle out, and the radius of the smaller circle is just r. So our sphere surface is like this, so our n hat's going to be coming out all around it like this. So n hat and e are both parallel to one another, so we're saying that e dot n hat is equal to the magnitude of e times the magnitude of n hat times cosine of 0, since they're parallel, and we're just left with e times n hat. So using Gauss's law, we can say that the closed surface integral of e dot n hat dA is equal to the sum of the total charges inside over epsilon naught. So we can pull our e out to the front, since it's just a constant, times dA, since we're trying to find we're doing the integral of dA, which will just give us e times a is equal to the total charges inside over epsilon naught. So then we use the surface area for a sphere, which is 4 pi r squared. So we're saying e times 4 pi r squared is equal to q times 4/3 pi r cubed divided by epsilon naught times 4/3 pi r cubed. So the reason we're using 4/3 pi r squared and then 4/3 pi r capital R cubed is because we're trying to find what the total charge within that area is. How much of it is the ratio of the charge within this area. So that's why we're using the 4/3 pi r cubed divided by the 4/3 pi r bigger r cubed. So then when we simplify that, we're left with e times 4 pi r squared is equal to q times r cubed divided by epsilon naught times r cubed. Since we're looking for the electric field, we're saying electric field is equal to qr cubed divided by 4 pi r squared epsilon naught r cubed. And then we get e is equal to qr divided by 4 pi epsilon naught times r cubed. And an easy way to check this, to check if our formula is correct, is we can check the units, and the units should be the same units as a point charge, which they are. So then find the charge on the outside. We have our sphere with the radius r, and then we have our bigger circle, since circles are easier to integrate, with our electric field going like this, coming out like all around it, since it's a plus q charge. Then our n hat, since the surface the surface of the sphere is also going outwards too, and since they're both parallel, it's just the same idea as before, is that cosine of 0 is equal to 1. So then we can say that using Gauss's law, that e dot n hat dA is equal to the sum of the charges outside divided by epsilon naught. So then when we do the integral of dA, we're left with EA is equal to the sum of the charges outside divided by epsilon naught. So then we can say that E times the surface area of the sphere, which is 4 pi r squared, is equal to Q times 4/3 pi r cubed divided by 4/3 pi r cubed times epsilon naught, and we're left with Q over epsilon naught. The same reason we're using 4/3 pi r cubed divided by 4/3 pi r cubed is that we're trying to find I guess I want to say the charge density within this sphere, and that will give us the charge density, the ratio of the charges. So then we can say that E times 4 pi r squared, we're looking for E, so we can say E is equal to 1 over 4 pi epsilon naught times Q divided by r squared, which is the charge, the formula for a point charge.